Okay, so what we're going to be doing today is looking at the investigative task from the test that you guys had over the weekend. So we're looking at question number 6. It says, the nerves that supply sensation to the front portion of a person's foot run between the long bones of the foot. Tight-fitting shoes can squeeze the nerves between the bones, causing pain when the nerves swell. This condition is called Morton's neuroma. Because most people have a dominant foot, muscular development is not the same in both feet. People who have Morton's neuroma may have the condition in only one foot, or they may have it in both feet. Investigators selected a random sample of 12 adult female patients with Morton's neuroma to study the disease further. The data below are measurements of nerve swelling as recorded by a physician. A value of 1 is considered normal, 2 is considered extreme swelling. The population distribution of swelling measurements is approximately normal for adult females who have Morton's neuroma. Okay. The scatter plot, so this is the first thing that we actually have to deal with here. It says the scatter plot of ordered pairs swelling in the left foot and in the right foot is shown below. The scatter plot suggests there are two distinct groups of patients. Patients with each group share a common trait. Use the scatter plot above and the table on page 10 to determine the common trait and explain how the trait differs for the two groups. So if you look at these scatter plots right here, one of the things that you'll notice is that there are two groups, and the idea that they're really going for here is that there's a group here and there's a group here, and you can say these are left foot and right foot, and so they're trying to get you to compare what's really different about these two. Why are some of these like down here for the left foot, you know, off to the side, and then up here for the right foot? Why are there these two distinct groups? And if you go back and forth and look, the one that's at, if you just go back to I'm looking at the front page still myself, so if you want to tear that off where you can look at it while you're looking at the scatter plot, the very first person is left foot dominant, and the swelling in the dominant foot is 0.41, so swelling in the left foot would be 0.41, and then the non-dominant foot is 0.10, so that's that dot right there. The next person is left foot dominant, and the swelling in the dominant foot is 1.55, so 1.55 would be over in here, and then 1.25, and so 1.25 would be up around here. So it looks like it's that dot. 1.65 and then 1.20 is the next one, 1.65 and 1.20. So that would be this, and that person is left foot dominant as well. And as you kind of go through that chart, the thing that you figure out is that all of these dots right here are from people who are left foot dominant, and all of these dots right here are from people who are right foot dominant. So what we can conclude is that the trait that distinguishes the two groups, so it wants you to suggest there are two distinct group patterns, share a common trait. And so what it wants to know is use the scatter plot above to determine the common trait and explain how this trait differs for the two groups. So the trait, the common trait that distinguishes the two groups is their dominant foot. The top group, the difference is the top group is right foot dominant, and the bottom is left foot dominant. Okay, and so what they were really looking for in this one was for you to say that the groups were different based on their dominance, okay? So there was a group with left foot people, or left foot dominant and right foot dominant. You could have gotten this one partially correct. It says if the response either identifies the two groups as people with greater swelling in the left foot and people with greater swelling in the right foot, but missed the connection of foot dominance, or states that only the dominant foot has more swelling than the non-dominant foot. That would have worked. So several people just pointed out the fact that one of them had more swelling. You know, this group up here had more swelling in the right. This group here had more swelling in the left. But the thing that tied it together, the trait, was the foot dominant. So that's what they were looking for there. Okay, and then part B maybe could have helped you a little bit because it says a scatter plot of the ordered pairs, swelling in dominant foot, swelling in non-dominant foot, is shown below. See, once they start breaking this thing up based on dominant foot now, no longer left and right, that could have been your clue to part A, okay, that there was some type of connection that dealt with the dominant foot. So maybe you could have gotten a little clue from that and gone back and worked on a few things in part A. Okay, now it asks what conclusions can be drawn from this scatter plot that are not apparent in the scatter plot from part A. So what can you see in this one that you couldn't see in the other one? And the thing that you can see now is that there is a positive linear relationship between swelling in the dominant foot and non-dominant foot. Okay, so before, there didn't really look like there was much of a pattern between the two. You can see these, you know, it seems to be pretty randomly distributed whenever they did it based off of left foot and right foot. But now when they switch it to dominant foot and non-dominant foot, it takes on this kind of linear pattern here. And so what you can see is that there is a relationship between the two. You could call it a positive relationship. You could say that as swelling in the dominant foot increases, so does swelling in the non-dominant foot. That would have been perfectly fine. But one of the main things that we're dealing with here is that there is a relationship between those two. And that's probably where I would have left it. But they wanted you to go a little bit further because you can see here that the swelling in the dominant foot is always greater than the swelling in the non-dominant foot. So they did want you to also conclude that swelling in the dominant foot is greater than swelling in the non-dominant foot. Okay, so that's what they were looking for there. And again, you can see that on this one, but you couldn't see it on the other one because the previous one was just broken into left foot and right foot. So there's no way to tell the difference in the swelling in the dominant foot and the non-dominant foot. So that's the two things that they were looking for there. All right. Part C. Can you conclude that there is a difference between the mean swelling, so we're looking for a difference in the mean swelling in the dominant foot and the mean swelling in the non-dominant foot for females who have Morton's neuroma in at least one foot? Give statistical justification to support your answer. Statistical justification. Anytime you see statistical significance or statistical justification, you know that what they're looking for here is for there to be some type of hypothesis test or confidence interval or something like that. And so what they're looking for in this case is a hypothesis test. That's how you give statistical justification. Just saying, hey, I think there's more swelling in the dominant foot. That doesn't help, okay? That doesn't help. So what you actually have to do is perform a hypothesis test here. Okay, so we're going to perform a hypothesis test. I'm going to come on down and we'll use Phantom. Let me write it this way. So parameters, first thing. So what we're going to do is we're going to set up parameters. We'll let mu sub d equal mean swelling in dominant foot. We'll let mu sub n equal mean swelling in non-dominant foot. Okay, and that's all parameters are. Okay, they just want you to write down any type of, symbols or variables that you're going to use and actually define them. So we'll define these two. So there's parameters. Hypothesis. Well, we're looking to see if there's a difference between these two things. So my null hypothesis, right? Remember, the null always says that there is no difference. So my null hypothesis in this case is going to be that the swelling in the dominant foot is equal to the swelling in the non-dominant foot. You could have written that a couple of different ways, okay? You could have said that the swelling in the dominant foot minus the swelling in the non-dominant foot would equal 0. Okay, but either way you want to do it is fine. And they just asked for a difference. They didn't say that one of them was smaller or greater than the other one. So our null hypothesis is just going to be that these two things are not the same. Okay, they're not the same. So there's our hypotheses. Assumptions. Okay, so we'll go next to the assumptions. Remember, we need something that is normally distributed. We need to make sure we have a simple random sample. And we also need to make sure that there is independence. Okay, so one, when it comes to a simple random sample, okay, we are told this is a random sample Okay, so you're good there. The next thing that you need is you need to make sure that this thing is approximately normally distributed, or that it doesn't have any really bad skewness and stuff. So we're told that the distribution, you could say this as well, because you were told that the distribution was normal. The distribution of swelling, is considered, where's the measurements, is approximately normal for adult females, okay, who have Morton's neuroma. Right, so the distribution of swelling is approximately normal, so we're told that the distribution of swelling is approximately normal. Right? And those are the two that they really wanted. You could have gone on to make a comment how, it's safe to assume that 12 is less than 10% of the total population of females with Morton's neuroma. Okay, so you could have said something about that as well, but the two conditions that they were really looking for is the fact that this was a simple random sample, and then also that this right here was excuse me, a normal distribution. And you could have said something, look at based on the trend line. So if you had graphed this thing out right here and looked at the differences, because what we're really concerned about here is the difference from the dominant foot to the non-dominant foot. So the difference in the dominant foot and the non-dominant foot, if you used it, you would see that you get a pretty good trend line, okay? The other thing that you could have done here, you may have said something about independence, okay? So we would say that the difference in swelling from non-dominant to dominant for each female can be considered independent. Okay, so that works too. And so our assumptions are done, and then name the test. Okay, so naming the test here seemed to be a little bit harder for some people, but the thing that you're really looking for here is the fact that we're using the same 12 individuals. Okay, we're using the same 12 individuals the whole time, and we're checking their dominant foot and the difference with their non-dominant foot. So this is a paired t-test. So I'm going to say, therefore, a paired t-test is appropriate. And again, this is because we're using the same person. We're not using 12 random dominant feet and 12 random non-dominant feet, okay? The dominant foot and the non-dominant foot came from the same person. And so these different feet are going to be paired together based on the one individual that both feet belong to, okay? So it's a paired t-test for that reason, because they go together. So we have named our test. So now we need to get test statistics here. So let's get our test statistics. And the way that we're going to do this one is we're going to use our calculator. Let me go ahead and pull this up. On. And what I have here is a list of data, right? So I have a list of data. So what I'm going to do is I'm going to go in to list, and I'm going to edit it. And in list 1, I'm going to put the dominant foot swelling. So 1.4, enter. And then 1.55. And you can do this with me as well. I'm going to leave the video running while I put these in, so feel free to go ahead and pull out your calculator and type these in as well. Okay, that's the 12 dominant feet, and then we got the non-dominants. All right, so you may be finished already because it's a lot easier doing them in the regular calculator than up here on the board, but I'm almost done. Okay, so we just got to go in and make this list here. And so there we go. We got 12 values for each of them. And so now I'm going to back out of here. And we're trying to run a test, so I'm going to go to stat. I'm going to move over to test. And remember, we're looking for a, we're trying to do a paired t-test. You can just scroll down until you find the paired t-test. And I don't see a paired t-test here. Ah, that's why. remember, when you do a paired t-test, what you're really looking for is the difference in between the two. So what I'm going to do is I'm going to go back into my lists here, and I'm going to go to L3, and what I'm going to do is I'm going to go up to the top, and in L3, I'm going to put in L1, that's my dominant foot, minus my non-dominant foot, which is L2. L2. And I'm going to let that come up in L3. And now the difference between the two is what I want to use. So that's the whole point behind the paired t-test. So there's not one that does it for you in the calculator. So you have to go ahead and run that into L3 and get the pairs. And now you can go into stat test. And now this is just a regular t-test. So it's just a t-test. And we will let mu be 0. And we will use not L1, but we're going to use L3. So second 3. We'll turn that into L3. And now, we want it not equal. And we'll calculate here. And now we get our test statistics. So we get a t-value of 10.681. We'll call it 0.682 if we round. And I like to do this. The degrees of freedom here is 11 because our sample size is 12. So if you put a little t sub 11, that lets them know the degrees of freedom. On most of the scoring guidelines, it doesn't ask for the student to actually have the degrees of freedom on there, but they do have them listed whenever they give the solutions. So that's what we're looking for. So here is t, and then we get a p-value of 3.811 times 10 to the negative 7. So that what that really means is that we've got 1, 2, 3, 4, 5, 6 zeros and then 3, 8, 1. Okay? So that's what we're dealing with back here. So this is a really, really small p-value. So what we've done as far as phantom goes is we've got our test statistic. That was the t-value. We obtained the p-value. And now we need to make a conclusion. And so remember, with your conclusion, you always want to link it to the p-value. So I will say since p is less than 0.01, there is strong statistical evidence to reject the null hypothesis, period. It appears that there is a significant difference, and this is what we're talking about. So strong, you can leave that the same for just about every question you answer. If p is really, really small, less than 0.01, there's strong statistical evidence to reject the null. It appears that there's a significant difference, because remember, the null says there's no difference. So if we're rejecting the null, we're going to say there is a difference, and a difference between what is the question? And the answer is swelling. In this case, we're talking about swelling in dominant and non-dominant feet for, I'm going to be specific with this, feet for marker troubles, feet for female patients with, I want to make sure I actually say this correctly. It's called Morton's neuroma. Okay, and there's part C. And the scoring guidelines for that one were pretty crazy. It wanted you to go through the whole hypothesis test. And I know it's kind of been the trend in the past that if it's, a part of a question, then they don't want the whole hypothesis test, the whole phantom. But if it's in an investigative task, then they're probably wanting you to do the entire thing. So go ahead and go through the whole process. It never hurts you to go through the whole process, so you can go through it all. And there were actually 4 components to that they were looking for. I'll tell you what they were. This was one component. This right here was the second component, but they were particularly looking for these 2 things. And then this was the third component. This was the fourth component. And in order to get an essentially correct, you had to have all 4, and then you could get a partial correct if you had 3 out of the 4. So had to do a lot of work for that one essentially correct there. All right, and now down to part D. So part D says the nerve swelling measurement is used to indicate whether a foot has Morton's neuroma. Use 24 measurements of nerve swelling to suggest a criterion for diagnosing Morton's neuroma. Justify your suggestion graphically. Okay, so that's an important part that they want us to actually, here's the question up here, justify your suggestion graphically. Okay, so they want us to make a graph, and then we want to use the graph to suggest a criteria for diagnosing Morton's neuroma. So what I'm going to do is I'm going to kind of go down here to the bottom of this page. Actually, I'm probably just going to use a new page, and I'm going to try to set up 2 different graphs. The one with Morton's neuroma and the one without. Okay, so let's do feet. So we'll do feet with Morton's all right, and I'm just going to make a dot plot here. So I'm going to start at 1 is considered normal. So this right here will start at 1. And they said 2 is considered, really bad swelling over in the first part. They said 2 is considered extreme swelling is the way they called it. So I'm going to do, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then we'll go to 2. And I'm looking for the one that actually has neuroma. So if you look at this first person, it says it's only in their left foot, so that's 1.4. The second person, it says that it's in their left foot as well, and it's 1.55. The next person, it's in their left, and their left foot is their dominant foot. That's how I'm getting this. So left foot is the dominant foot, so that's 1.65. The next person says they have it in both feet. So I got to use the dominant foot and the non-dominant foot, so 1.55 and 1.4. The next person is left only, and that's 1.7. The next person is both, so that's 1.85 and then 1.5. Next person is right, and their right foot is their dominant foot. So dominant foot's right foot, neuroma's in the right foot, so that's 1.45. Next person is 1.65. Next person is 1.6. Next person is 1.70, and it's in both, so 1.70 and 1.45. And then the next person is in both. It's 1.85 and 1.45. And then the next person's with both. That's 1.75 and 1.6. Okay, so this is what our dot plot looks like. Okay, and then it would be a good idea to go ahead and do the other one. So we'll do the feet without. And I'll just do it on the bottom side of this same dot plot. By the way, we need to label this, okay? So I'll just call this swelling. So these numbers right here represent our swelling. You want to make sure you get a label. Not a bad idea. Tell you what, let me just do this. I'll put swelling down here, and we'll just do another plot. Just go ahead and make another one. So from 1 to 2. Okay, and then we're looking for the ones that don't have Morton's neuroma. So for the first one, that's a 1.10, and then the next one's a 1.25, the next one's a 1.2. The next person had it in both, so skip them. The next person is a 1.4. The next person was both, so skip them. The next person is a 1.2. The next one is a 1.3. The next one is a 1.4. The next is a 1.45. Nope, that person had both. The last 3 people all had both. So that's it for the feet without Morton's neuroma. Let me make sure I get a label up here. This is, I'm going to move this to the top. I'm going to move this up here. Too bad you can't just move it like this on your paper, right? Here in swelling is what we're measuring down there with those numbers. Okay? And so here's a graphical display. And if you compare the two, you can see that all the ones with Morton's neuroma have, 1.4 or more, and the ones without are 1.4 or less. So we could say swelling of 1.4 or more indicates Morton's neuroma. Okay? So swelling of 1.4 or more would indicate Morton's neuroma. And that's what they were looking for on the scoring guidelines. You could have messed up part D if you didn't label stuff on the graph, but D says that it's essentially correct if the response recommends a reasonable criterion for deciding whether a foot has MN based on the data and justifies the criterion graphically. There are other possibilities for graphs than the 3 outlined, so they gave a couple of things that you could have done. But the plot should make it easy to compare the measurements in the feet with and without Morton's neuroma. Communication must be strong. So you could have come up with another criterion. As long as it was legitimate, they would take it. So all you had to do was just make sure that what you were doing was, somewhat legitimate. So those are the FRQs, and now we will move over to the multiple choice questions. So the multiple choice questions are coming up. If you want to go ahead and grab those. Your packets are in the room. Maybe you have those already. If not, you want to go ahead and get those. But the packets with all of the multiple choice questions in them are laying there. So make sure you grab one. And then we're just going to go through a select few here. And so we'll start with, everybody did really good on most of these, but the first one we need to talk about is actually number 11. So go ahead and flip to number 11, and I'll read the question and we'll get. All right, it says, Julie generates a sample of 20 random integers between 0 and 9 inclusive. She records the number of 6s in the sample. She repeats the process 99 more times, recording the number of 6s in each sample. What kind of distribution has she simulated? Okay, so all she's looking for is 6s, right? So one of the keys here that might really help you is to think of the fact that you either get a 6 or you don't get a 6, right? And so she's not worried about any of the other numbers but a 6. So there's a possibility of getting a 6 and not getting a 6. So since those are your only 2 possibilities, either success or failure, 6 or not, then what you're actually going to get there is a binomial distribution, right? Because it's either 6 or not 6. So it's a binomial. And the probability, if you have numbers 0 to 9, that's 10 numbers, right? And a 6 is one of those. So you have 1 out of 10 chance, or 0.1. So it has a probability of 0.1. And so now at this point, you're down to either C or D. And the question is it a distribution with n equals 20 or n equals 100? And the correct answer is n equals 20. And the reason why is because there are 20 integers in each one of the simulations that she's doing. The 100 is the number of simulations, right? The 100 is the number of simulations. It's the number of times that she ran this distribution, a distribution with 20 values and an expected value of 2 in each one of them, but the probability is 0.1. So she ran 20 values with a probability of 0.1, and she did that 100 times. So the 100 there is the number of times the simulation was done. The number of numbers in each simulation would just be 20. Okay? Next up on the list is number 17. So go ahead and flip to number 17. All right, so number 17 says, excuse me, in an experiment, 2 different species of flowers were crossbred. The resulting flowers from this crossbreeding experiment were classified by color of flower and stigma into one of 4 groups as shown in the table below. And you can see them there. A biologist expected that the ratio of 9 to 3 to 3 to 1 for the flowers in types 1, 2, 3, and 4 respectively would result from the cross-breeding experiment. From the data above, a chi-squared value of approximately 8.04 was computed. Are the observed results inconsistent with the expected ratio at the 5% level of significance? Okay. So this may be a little different than something we've talked about before, but let's say we've got a chi-squared distribution, right? And so we've got a chi-squared distribution here. And if you think about it like if it was a normal distribution, what we always do is we have some type of target that we're trying to hit, and we're trying to figure out how far we are away from that target. Okay? And so what we do is we set up a rejection region out here. So for example, if it was a normal distribution, and the rejection region was at the 5% level of significance, then we would let alpha equal 0.05, but the z-score we would need to get out there, right, to have 5% level of significance. Well, let me do it for 0.025, right, because there'd be 0.25 on each side, would be 1.96. But this z-score right here is the critical value. If we get a z-score more than that, then we're going to land somewhere out here, and that's in the rejection region. Well, the chi-squared score that we just got is 8.04. So what we need to do is we need to find what percent of the data lies out here beyond 8.04 in the chi-squared distribution. So I'm going to go to my calculator. See if I can get it on. Clear this out. And we're going to go second distribution. And what we're trying to figure out is how much is out in the chi-squared distribution. So I'm going to use a chi-squared CDF. And so I want to know how much space is out there or on the right side on the chi-squared CDF. So I want to go from 8.04 to, and now remember for a chi-squared, we're going to go all the way to 1,000. There's a lot more stuff out there. Degrees of freedom in a chi-square test is the number of categories minus 1. So in this case, it's 3. And I'll paste that. If you have a calculator that looks like this is what you would want to look at. The first value, comma, the second value that you're trying to go to, comma, and then your degrees of freedom. And if you put that in, you get 0.045. Okay? So what that means is that less than 4.5% of the data lands beyond 0.084. So there's some other chi-squared value, right, that would be perfect for right here. Let's say maybe it was 7, okay? But since our chi-squared value passed the 7 and went out to the 8.04, we got a region, a percentage here, and from 7 back, the percentage would be 0.05. But as it stands, we got a percentage of 0.04 because we started here. This is how much percent of the data was to the right of the chi-square statistic that we got. So our chi-square, our p-value is too small, but our chi-squared value is too big, because the reason why we ended up with such a small area, the area back here is our p-value, is because our chi-square value was too far over. So the answer is yes, it is inconsistent. We would reject a null hypothesis in this case, right? Because our p-value is small, but it's because the chi-squared value is greater, right? The chi-squared value is greater than whatever the critical value would be. So the answer to number 17 should be A. All right, next up on our list is number 19. So you can turn the page one spot there and have a look at number 19. It says, a delivery service places packages into a large container before flying them across the country. These filled containers vary greatly in their weight. Suppose the delivery service airplanes always transport 2 such containers on each flight. The 2 containers are chosen so that their combined weight is close to but does not exceed a specified weight limit. A random sample of flights with these containers is taken, and the weight of each of the 2 containers on each flight is recorded. The weights of the 2 containers on the same flight, and then it wants to know about their correlation. Now, this is a, when we talk about correlation, hopefully that sparks into your mind that we're dealing with a linear regression here whenever we talk about correlation. So let's call them heavy package and light. And let's say that the plane can take 1,000 pounds. Well, what can happen is the first one can weigh 1,000 and the second one would have to weigh 0. And we can call them heavy and light. We can do this whichever way you want to. Let's just call them A and B. Maybe that'll be easier to think about it if we just call them A and B. But if we get B to weigh 1,000, then that means A has to weigh 0. So we have this line right here where the combination of the 2 points, the point right here in the middle would be the point 500, 500, right? Because the combination of those two would weigh 1,000. And so this is the line that we can't cross. So this is kind of how you want to think about it. If package B gets heavier, okay, so let's say that package B is the distance from this red line. Package A's weight is the distance from this blue line. Well, as we make package B heavier, so B is going to come from the red line out to here. Well, in order to make that work, what we have to do is package A, package A would be here. So what would have to happen is, if we're going to make this work, then package B it has to drop below that line. So in order to make it work, package A's weight had to drop. In the same way, if you wanted to make package A really heavy, so A is going to be really heavy. So that's the point that you're going to have for A, is this one here, okay? The only way to make it work is to scoot package B closer to the line. So as one of them gets heavier, the other one has to get lighter. So that is a negative correlation. As one goes up, the other goes down. So the answer to number 19 is B. They would have to have a negative correlation. If one package got heavier, the other one would have to get lighter. Okay, next up on our list is number 25. So go ahead and flip, and we'll look and talk about number 25. It says, when performing a test of significance about a population mean, a t-distribution instead of a normal distribution is often utilized. Which of the following is the most appropriate explanation for this? The sample size is not large enough to assume that the population distribution is normal. The sample does not follow a normal distribution. There is an increase in the variability of the test statistic due to estimation of the population standard deviation. The sample standard deviation is unknown. Or E, the population standard deviation is too large. Okay. When do we use a t-distribution? Remember, a z is for normal. So when do we use a t instead of a z? Well, the answer is when the population standard deviation is unknown. And so this is that's what they're saying in part C. There's an increased variability of the test statistic due to an estimation of the population standard deviation. We don't know the population standard deviation. And so what we do is we use the sample standard deviation. E is ridiculous. D is ridiculous. You can always get the sample standard deviation. You have the numbers in front of you. The thing you can't get is the population parameter. You can't get the population standard deviation. So what we end up doing with a t-test is we use the sample standard deviation to estimate the population standard deviation. But we don't really know what the population standard deviation is. Therefore, we kind of increase our variability by using a t-distribution. It's gonna cause for a wider range of numbers when we're talking about a confidence interval or a hypothesis test to make up for the fact that we don't actually know the population parameter when it comes to the standard deviation. So C is the correct answer for number 25. All right, after number 25, we're over to number 27, so you can flip the page once. Number 27. It says a t-statistic was used to conduct a test of the null hypothesis. H naught says that mu is equal to 0 against the alternative hypothesis that it doesn't equal 0. So that's a two-sided test because they just said it doesn't equal 0. The p-value was 0.056. Now that p-value is for a two-sided test. A two-sided confidence interval for mu is to be constructed. Of the following, which is the largest level of confidence for which the confidence interval will not contain 0? So what we're looking for is for this confidence interval to not contain 0. So we don't want the p-value to overshoot, right? So we want this thing to work out. The key here is that the p-value of 0.056, okay, has already been used as a two-sided. So there's no need to double that. Okay, it is the way it is. So which one of these confidence intervals wouldn't catch this p-value right here? The biggest one that wouldn't catch it. Well, if you do a 95% confidence interval, then you would get 0.05, right, as your as your critical value. And so this p-value right here would be too big. You would not reject the null hypothesis. So it would contain 0. But the largest one that would not contain 0, if you did a 93% confidence interval, then you would have 0.07, okay? 0.07 right here would be your cutoff. And so this right here, the p-value would be smaller, and so it wouldn't contain 0, and you would reject the null hypothesis is what would happen. So B is the one there. I think the confusing part might have been trying to double that p-value, but there's no need to double the p-value, and we don't want to catch, we don't want to contain the 0, so we want to be able to reject the null hypothesis. So the correct answer for number 27 is B. All right, after number 27, we're down to number 30. So go ahead and flip over one page to number 30. We'll take a look at it. It says, a researcher has conducted a survey using a simple random sample of 50 registered voters to create a confidence interval to estimate the proportion of registered voters favoring the election for a certain candidate for mayor. Assume that the sample proportion does not change. Which of the following best describes the anticipated effect of the width of the confidence interval if the researcher were to survey a random sample of 200 rather than 50 registered voters? Okay, so the thing you got to think about here is what's going to happen to the standard deviation, because nothing else is going to change. But remember, or I should call it the standard error. Remember, we always do sigma divided by the square root of n. And what they're saying is, what they're going to do is they're going to take 50 voters, and they want to know how that's going to compare to if they took a sample of 200. What's that going to do to the confidence interval, right? Because remember, we always have a z-score times this, a z-score times that. right? So the confidence interval is mu, but this is staying the same, this is staying the same, this is staying the same. The only thing that's changing is what we're dividing by. So what you really need to do here is compare the square root of 50 to the square root of 200. Okay, so I'm going to go on here. I'm going to say second square root of 50, enter, second square root of 200. And if I compare those two, okay, it looks like 50 is, the square root of 50 is half of the square root of 200. So this is, sigma over 7. This is sigma over 14. So if I divide by a number that's twice as big, 14 is twice as big as 7, then what happens to my answer is it gets cut in half. And so the correct answer is B, that the width of the new interval would be about 1/2 the width of the original interval. So it would get cut in half on number 30 there. All right, next up is 32. So it's just a simple flip of the page. We'll go over to number 32. All right, it says that an independent research firm conducted a study of 100 randomly selected children who were participating in a program advertised to improve mathematics skills. The results showed no statistically significant improvement in mathematics skills using an alpha level of 0.05. The program sponsors complained that the study had insufficient statistical power. Assuming that the program is effective, which of the following would be an appropriate method for increasing power in this context? Okay, so when we talk about power, remember that power is the ability to get rid of a bad null hypothesis. Okay, so it's the ability to get rid of a bad null hypothesis. So, one of the things that you can do, if you remember this little crossover here, okay, is that if you, let's just say that this is a critical value here, and the null is actually true. This one right here is if H naught, or H alternative. The alternative is true, sorry. And here's the critical value. So what we need to do is make sure, and then if this is true, then what we're looking at here is if we get something down here, so the critical value would be, here, if the original hypothesis is true. But the whole idea is that if we get something down here, the alternative hypothesis is the one that's actually true. So this one doesn't even matter anymore. But if we get something that's way down here, remember this one was over here. If we get something way down here, what we're going to think is that we got one from this other distribution that says that the null hypothesis is true. So the problem with this test, okay, so this is the power. This is the likelihood, all of this area over here is the likelihood that you draw a sample that causes you to reject the null hypothesis. So the problem is that we got something over here, okay? We got something over there instead of something over here in the middle. So what we want to know is how to fix the problem of getting something over here. How could we reduce the chances of getting a sample that's way out there on the outskirts? So a two-sided or one-sided test here is not really that important. Increasing the alpha level to 0.01 is not going to help our cause, because that's dealing with this one. If we increased the alpha level over here, okay, then that's not gonna change anything as far as the power goes, because it's dealing with the null being true. But what we could do is we could increase our sample size, because they took a sample of 100 students. So the likelihood of you getting something way out here when you use 100 students is a lot higher than if you use 200. Remember, if you get 200, what it's going to do is it's going to squeeze this data set right here together, okay? And so as this data set gets squeezed together, it gets closer, then what's going to happen is the point that you would get to out here would be further away. It would be more standard deviations away. So increasing the sample size increases power. Now that may be just something that you want to remember. If you increase the sample size on a test, then you increase the power of the test. Okay, it makes you more likely to get rid of a bad null hypothesis. All right, so that's 32. Next one is 35. So let's go over to number 35. It says a group of students has 60 houseflies in a large container and needs to assign 20 to each of 3 groups labeled A, B, and C for an experiment. They can capture the flies one at a time when the flies enter a side chamber in the container that is baited with food. Which of the following methods will be most likely to result in 3 comparable groups of 20 houseflies each? Okay, so 60 flies in a large container, and they need to get them separated into groups, and they can bait them so that they can get them one at a time instead of all in a big group. Okay, it says label the first 20 flies caught as group A, the second as 20 as group B, and the third as group C. That's no good, because that's kind of like a convenient sample, right? All you're doing is you're taking the first 20 and the second 20 and the third 20. Well, if you're baiting them with meat, what if there's some difference? The first 20 are the ones who want the meat really bad, next ones who don't want it as bad, and the last ones who don't want it much at all, right? So there could be some difference in the flies that come through the door first compared to the flies that come through the door last. Maybe the stronger flies get to the door first and the weaker ones get to the door last. So you want to make sure that you don't just take them in groups like that. B, write letters A, B, and C on separate slips of paper. Randomly pick one of the slips of paper and assign the first 20 flies caught to that group, the next 20 to the other group, and the remaining flies to the remaining group. That's the same thing again, except now instead of the first 20 being group A, the first 20 could be group C. It's still the first 20 flies. It doesn't matter that they're called group C instead of group A. C, when each fly is caught, roll a die. If the die shows an even number, the fly is labeled. If the die shows an odd number, the fly is labeled B. And when 20 flies have been labeled A and 20 have been labeled B, the remaining flies are then labeled C. No, because the same thing's happening here. Group C is still just getting all the weak flies or the flies that don't want the meat. And so group C is not evenly in the mix. D, place each fly in its own numbered container, numbered from 1 to 60, in the order that it was caught. Write out the numbers from 1 to 60 on slips of paper. Put the slips in a jar. Mix them well. Pick 20 numbers out of the jar. Assign these flies in the containers with those numbers to a group A. Pick 20 more numbers and assign the flies in the containers with those numbers to group B. Assign the remaining flies to group C. All right, that sounds pretty good because you get one fly at a time, and each fly could end up in any group based on the numbers that come out of the jars. And a key there, too, is that you evenly, right? You get 20 in each group because it wanted you to get comparable groups of 20 in each group. E, when each fly is caught, roll a die. If the die shows 1 or 2, the fly is labeled A. If it shows 3 or 4, it's labeled B. If it shows 5 or 6, it's labeled C. Repeat the process for all 60 flies. That one sounds pretty good too. So, you know, you got a chance, each fly has a chance of being in group A, group B, or group C. It doesn't matter what order they came through the door. The only problem is that if you repeat that process for all 60 flies, there's nothing in that process that prevents you from getting 22 flies in one group, 21 flies in another group, and 17 flies in the last group, right? So you got to make sure you get 20 into each group, and that's a good randomization there, but it doesn't get the groups evenly at 20. Let me make this comment. Even groups of 20 is not important for you to be able to run an experiment and stuff. But in this case, they did say specifically that they wanted even groups of 20. So that's why you're actually trying to take care of that. Okay. Otherwise, splitting them up like that wouldn't be too bad of an idea. Okay. So the last, and I've been going through the ones that double-digit numbers of people missed. So the last one that at least 10 people missed would be number 39. So go ahead and flip to number 39. And it says, a polling organization asked a random sample of 1,000 registered voters which of 2 candidates they plan to vote for in an upcoming election. Candidate A is preferred by 400 respondents, B is preferred by 500 respondents, and 100 respondents are undecided. George uses a large sample confidence interval for the two proportions to estimate the difference in the population proportions favoring the two candidates. This procedure is not appropriate because the two sample proportions were not computed from independent samples. B, the sample size was too small. C, the third category, undecided, makes the procedure invalid. D, the sample proportions are different, therefore the variances are probably different as well. George should have taken the difference and then used a large sample confidence interval for a single proportion instead. If you want to find the difference between two proportions, then you have to use two separate proportions, two different samples. So E is out. The reason that this one's invalid, and the tempting thing here is to say C, that a third category undecided makes it invalid. But that's okay. If we're talking about the proportion of boys who like football, and I gave you an option between football, baseball, and we'll say soccer, and let's say that for boys, 0.2, or it's probably higher than that. We'll say 50% of boys like football, 25% like basketball, and 25% like soccer the best. And then we did girls. And we did, let's say that 30% of girls like football, 40% of girls like basketball, and 30% like soccer. Does basketball and soccer keep me from being able to compare the proportion of boys and girls that like football? Absolutely not, because I'm talking about football. It doesn't matter that there's another category here, okay? So, but what you need two different groups of people if you're going to find a difference between them. And so the problem here is that they only took one sample of 1,000 adults or voters. They didn't actually take two separate samples to see how two different groups felt about it. So the correct answer there is A. The reason it's not valid is because the samples aren't independent of one another. If somebody voted for, if somebody in the first group said that they were going to vote for candidate A, then they automatically couldn't vote for candidate B. And so those two samples, what happens in one of them affects what happens in the other. So they are not independent of one another. So that was the problem there. All right, so good luck studying and getting ready for the practice exam that you guys are going to have tomorrow. I hope that this was helpful for you. So study up tonight and make sure you're ready to go tomorrow.